In our lecture last time, we actually managed to make quite a lot of progress in terms of summarizing all of our observations about the forces on charges moving near wires into one very simple relationship and one very straightforward result for an infinite wire carrying a current. In particular, we learned that there's a new field out there, a new property of space that can have some influence on particles moving through it. In this case, it's what we call a magnetic field, to contrast it with the electric field. And what we learned is that there's this new force that we haven't seen before. It's somewhat analogous to the electric force, which is just charge times the electric field. But we know it can't be exactly the same force or the same field because now the force depends upon the velocity. This is sort of the velocity-dependent part of the force on a particle moving through an electromagnetic field. And we learned that this force is proportional not only to the charge, but its velocity, and then to this particular property of space, which we call the magnetic field. Taken together, this law for the force from the magnetic field with this law for the force from the electric field gives a complete description of electromagnetic forces. So we have this nice simple way to calculate the force on a moving particle. The second result that came out of our discussion last time was a particular result for the form of the magnetic field for just one situation. So far, this is now the only situation for which we actually know the magnetic field. And that's when we have an infinite wire, as I'm showing to you here, of current flowing to the left along the minus x direction. And when we are directly above that wire at a distance r, this magnetic field is a vector. It points directly into the board, as I've indicated here by our standard X symbol, like an arrow whose tail feathers we see flying away from us directly into the board. It depends as this fundamental constant mu naught divided by 2 pi r, and then if we have a proper right-handed coordinate system, as I'm showing you here, the direction is into the board, which is the minus z direction, which we indicate by a minus k hat.